don't know. Let me look at that. I never thought about that. Okay. What? Never seen that. I should do YouTube. Maybe there's something wrong with my computer. Okay. Everything very slow. Okay, let's see. Wait, let's see. I'm trying to think. It's too early in the. Where is it? Do they have a date associated with it? Oh my gosh, it's slow. Okay, well, I'll figure that out later. So here, I'm going to leap into energy section, chapter 14. And what you'll see is that there's a significant advantage to using energy methods over all the others. And that is, one, the problem level of complexity goes down considerably. And then because of that, the number of problems you can work or with this expands pretty high. So on this whole chapter is constructed in an interesting way. So I'm going to go through the whole thing, then I'm going to break it down and show you a different way of thinking about both ends of this. And that is relates us or takes us towards the area of thermodynamics. So he starts with this concept of work of a force. It turns out that it's associated with the force and the direction it moves. So if I put a box on the table and push it, it has a little bit of friction. It doesn't have to have friction. And then I move it. And so as a matter of fact, let's take the friction off for right now. So I move it with 10 pounds. I move it, say 20 feet. Then the direction it moved, or the dr, was in the direction of the F. So if you take the F and then the dr, and the angle between them is 0, then what you find is F dot dr is just F dr, and the cosine is 0. So it's just that. If in fact the friction force were there, then that force is opposite to the direction. So it becomes minus. So putting work in plus taking work out of the system is minus. So what he does here is he takes a look at that, and in the context of, just a block moving across the screen here, that's fine. But let's take a look in the case of, say, spring K, and in a normal spring, what you do is F is equal to the K of the spring times the deflection. So if you're going to pull it one way or another, you have, let's see, F and some deflection. So in this case, where the block was slid across the distance, what happened is F remained constant. It moved a certain distance, or I'll use the concept he said, dr, and therefore that is the work. But if you've got a spring, the more you pull it, the tighter it becomes. So what you end up with is the area here becomes K delta squared over 2. And the K, okay, so this is F at the top is equal to K delta. This is just delta. So if I want to know the area here, I multiply this F times this delta and divide by 2 because I'm missing this area right here. So it turns out F is nothing more than K delta squared over 2. So you've seen that where the energy in a spring, maybe you've seen it, is 1/2, or you could say K delta. I don't know how he presents it in the book. Oh, well, here we got they do have the dates on them. I may stop putting the dates on. Let's see if they do have the dates. Oh, that's a difference. I'll worry about that later. They do have the dates on them. So you go back to the book. He goes on. He starts talking about possibly an odd angle here, and he basically describes this as being the energy. If you have a constant force, a constant area, this is, I'll go back and look at this. This is the weight, and if the weight is going down in the y direction, then the only energy is if you took the ball there and you moved it down, or you moved it up. You moved it to a higher plane, what they're going to call potential energy is higher than, say here, potential energy middle, and then potential energy the lower part. So believe it or not, that's nothing more than the same thing. Look at the spring, you get the same thing. Here is even a better rendition because maybe the spring was pre-compressed. That happens a lot. In the old days, they had pinball machines where there was a little pre-compression there. And you would impart energy on the ball by pulling that spring back and letting it go. So the energy there is slightly different than 1/2 K. In his case, he's using S. S squared, it turns out to be S2 squared minus 1/2 K S1 squared. It's basically the area inside there. And then there'll only be one other thing, and that is, okay, so if you look at this, okay, this is essentially a form of Newton's equation. If you look at it, F is equal to ma, right? But actually, it was written originally like this. The problem with displaying this to the general public is before you even talk about this, you have to define what these do's, because that's the first thing somebody's going to ask you. But there's no derivative term here, so you can display that equation just like E is equal to mc squared. You can display that equation to the general public. There's no differential there. So the general public can actually read a website, or somebody can go read a website about that. This was the original form of it. In fact, the next chapter deals a little bit more with this, and we'll come back to this. But if you look at it, you're going to see a form of this, and then you're going to see the energy might change. This kinetic energy. Kinetic energy might change from state 1 to state 2. Here he's defining state 1 and state 2. Now, this is a part that, you can stare at and look at or ignore it. I'll come back to it, because what happens next, here, give us a few minutes. He goes in and talks about this. He goes in now and talks about friction. Now, one of the things about friction is it's losing energy. So this block is sliding from left to right. If there's friction, the carpet or whatever it is might warm up there because of that. So as you move, the frictional force takes away the energy. It's not the only one that can take away energy, which we'll talk about that too. And then he goes through problems, and then he comes back in the next section, and he almost repeats himself. Okay, let me get to the next section. Except he'll start talking about, okay, so here's power and efficiency. Power is nothing, energy per unit time. So in other words, if you walk up 9 flights of stairs, you're going to have a set amount of energy. But somebody who walks that 9 flights of stairs in 1 hour may actually breathe very normally the whole time. Somebody who runs that set of 9 floors in 15 minutes is going to be putting out a lot of power, because the same energy over 15 minutes versus this person putting out the same energy over, 60 minutes. This person put in a lot more power. So, and the reason I talk about 9 floors is that's what I used to do when I was teaching in New Orleans. So, section on that. Then we get into conservative. Now, there's no difference. Here's what's so funny. This is what confuses people a lot. If you look at it, conservative forces and potential energy. Okay, conservative forces means if you took the ball, moved it up to here, and then to here, and then back down to here, you would have the same energy of the system. Nothing was dissipated. So there's no loss of energy. So conservative forces give you that. So gravitational force, yes, that qualifies. Actually, it doesn't have it, but also electric fields also are that way. Electric fields, which are basically very much like gravity, except the thing is, if you put an electric field and you have something that is a magnet, move it back and forth, you're going to experience almost the same feeling as gravity. Elastic potential. If it's truly elastic and it's not losing energy as it's being stretched and then compressed, that's a conservative. And then you get this thing called the potential function, and then believe it or not, you'll go down and get a U, and then it'll have the equation maybe a little lower. Here he's talking about a field equation. This essentially deals with something like gravity or electric field. And this is all great. You have a slightly different equation. But now what I'm going to do is I'm going to go in and show you the way to think about this going forward. And what I mean by this is setting you up for thermodynamics. Let me go back to a problem. And that's essentially it. That's the end of the chapter. If you go Past that, you're not going to see, first of all, if you could see it at all, conservation energy. And then what you're going to do is all of a sudden you're going to see bags and bags of problems, and then a review session at the end. So let's go. Maybe I can use the mouse to move myself quicker. Let's go work a problem and show you a different way of approaching it mentally, that actually may be more beneficial in line with what you're going to see in your future. So let's pick a problem. I don't know which one. These are the fundamentals. Yeah, let's just pick this one. I mean, okay, I think I hit the button. Okay. Let's go ahead and do. Okay, so what I'll do now is I'll just select everything, delete it, drop the problem. And now, so the first thing I'm going to identify is two individual states. So this is exactly the verbiage they use in Thermo. So I'm kind of setting you up for Thermo a little bit, although it's not going to be complete. They're going to go deeper into it. So states are associated with two specific locations of all the objects. There's an A and there's a B. When you get into Thermo, it may be a fluid flowing from A to B. So it won't be just a collar. It'll be like all the particles of fluid going from here and then to there. So it comes a little bit different, but it's very much similar. It says a 5-pound collar, which I guess that's that thing, is folded with a cord that passes over a peg here. The cord is subject to a constant force of 10 pounds. The collar is at rest when it's at A. Determine the speed when it reaches it. Now it says neglect friction, so I'm going to assume there's no friction in this and no friction over that little, whatever that thing was called. I guess he's calling that a collar. So I'll call that a frictionless pulley or something. So the energies that you have in a complete sort of sense, 1/2 mv squared. This would be the kinetic energy. Oops, that's not the, it's not a K. This would be the kinetic energy. You might have a mgh, and this is associated with a potential energy, and I'll just put a subscript 1, and then 1/2 K delta squared, and that would be the potential energy. I'll put for a spring. How about for G for gravity? And that's pretty much it. So you might have this and this and this. In this case, I don't see any springs, but I'm going to just keep it in there because of that. Okay, so I'm going to write it, energy at state A being 1/2 mv squared. This would be A plus mgha plus 1/2 K delta squared at A. But guess what? There's no springs, but I'm going to write them anyway. Now, there might be some kind of weird force, and he puts dr, but I'm going to just do an r. So there might be multiple forces. So if there's multiple forces, I better put a sum here. This is an important term because what I did, okay, this is the energy at state A. This is the energy that is either added, or subtracted from state A to state B. Now he has a term in there that he may use. I think it's UA to B or something like that. I don't even use the notation he's using because I think it's maybe maybe it's a good idea to think about what it is, except focusing on what term you're using, because when you get into thermo, depending on the book, they may actually use a different term. Okay, so here he's kind of calling it this, which, you know, in thermo, they may actually call it just E, 1 to 2. So just be aware that what we're talking about is the energy either added to or taken away from state 1, in this case, to state 2. And so that's all this is. So I'm not even going to use this term. I'm just going to say that all those energies end up being something like that. When you get to thermo, there may be other forms of this, but the concept is you started at, this is a state, or in our case, a location. In thermo, energy state, a location, and then what we're going to have, we add or subtract energy, and we're going to end up at B. Now, I'm going to cheat in the sense that I'm going to just take this and do a copy and just drop it over here and move it up here. Then guess what I'm going to do? I'm going to go ahead and change this to B, B, and B. So now what we are doing okay, this is state B. So this is energy state B, or in our case, location, because it's always kind of associated with the location, even in thermo, because you may be looking at the inlet at one location and an exit at another location. So, you know, may actually be associated with a location there. So that's what you got, and that's all you really need. Now, you can go back and pick hairs over T, you know, okay, so there's it is true, there's a kinetic energy version of it, and there's a potential energy version of it. And we can get hung up on that, and that's important to recognize. But what I'm trying to do is lay the foundation that we start at all the energies at A, we add or subtract the energies, and we end up at B. How we got there is depending on the problem state. So with that in mind, let's go ahead and take this whole thing. Now that I've kind of monkeyed around with this, let's take this, move it to the side, and then I'm going to copy it and use portions of it. Actually, I should have just copied it. But you know what? It's still selected, so I'll copy it. I'll go back over here. I'll drop it. And now I'll start systematically erasing things. Here, I'll just use the eraser. Here. Just, I have no spring. Let's see. I'm going to get rid of the box. Get rid of this. I still have no spring on the right side either. And so now I can sort of select this thing and kind of put it together a little better. Uh-oh, what happened? Okay. That was, okay, so wait a minute. I was supposed to be in that. Okay. Okay. And okay. So what does he say about our problem? He says, I'm going to shove it up there as close as I can so I can zoom in. He says, the collar is at rest. Collar is at rest when it's at A. That means this velocity is 0. Believe it or not, okay, so if I'm starting to deal with these terms, then I have to see, okay, I'm going to make the assumption that gravity is pulling this way. So what I have to do is make a datum and list these as the Z's, or I could list them as a H. But in any case, what I find out is that the collar did not go up against gravity. This thing isn't looking like this. The energy, the potential energy here is the same as it is here. So this term equals to that term. So essentially, since this is 0, all I get is sum of the forces times the distance displacements there. It's equal to 1/2 mvb squared. Now, here's the key. Okay, you gotta, this part's pretty easy. Okay, so I'll deal with it first. And that is 1/2, I think it's 5 pounds. So if I want to turn it into a mass, I have to do that. And velocity would be squared, and I'm done. There's nothing more for me to do because the goal is to find that. Okay, so if I can find that, I've got stuff. Now the key is looking back in here. If I look at this, okay, we can look at it the hard way or the simple way. Here's the hard way. Okay, I'm pulling this with 10 pounds. Here's 10 pounds. If I want to look at it, it's basically like that, but this vector stays the same length here. And so this vector that's in the direction of movement eventually goes to 0 here. However, if I went and painted a piece of, or wrapped, say, a piece of electrician's tape here, pulled it with 10 pounds and moved it a certain distance, you could do it. If you feel like doing it, I'd say have at it. But whatever this distance we move, times that 10 pounds will be equivalent to integrating this or finding this value, this component, dotted with the movement at that point. And one day, if you feel like you don't have anything better to do, I would say go prove that to yourself. So in other words, I'm going to focus on what happens here, not what happens here. The difference is this distance is 4 foot. This is 3. This is not 3 or 4. So what is it? Well, it turns out, okay, so the rope, this distance was 5, and this distance is 3. So if you have a rope that was 5, and it got pulled to the point where it was 3, then this distance has to be 2. And so, and again, I'll repeat myself. The distance from here to here is 5 because this is a 3, 4, 5. The distance that the rope ends up at right here is 3. So essentially, this piece of tape that I wrapped around the rope moved 2 feet to the left under the force of 10 pounds. So the key is it moved in this direction and it was pulled in this direction. Since it was moved and pulled in the same direction, the dot product is positive, and this whole thing just becomes 2 times 10. Wasn't it 10 pounds? Yeah, 2 foot, 10 pounds. So 20 foot-pounds is equal to, oh gosh. Okay, so hang on. Let me do this. There. So the other thing is you're sitting on this other side and you're looking at your units. This unit should be slugs, and this unit should be a foot squared per second squared. However, from F is equal to MA for units, you would find a pound is equal to a slug times a foot per second squared. So if I look at this really close and compare it to this, then that thing should be a foot, well, a pound foot pound, which is the same unit as back over here. So if you want to find the velocity, all you do is take this 20 multiplied times 32.2, and I got 2 in there as well, and divide by that 5, and take a square root. Did I do all that? I think I did all that okay. And this thing should be able to do that. 16.05. So. But I think the key here is not so much the number as it is the approach, that you're starting from a state one, from, in this case, state A to state B, and going from A to B. I had energy, all my energies at state A, all my energies at state B, and then everything that happened in between those two. And so it's that simple. You can make it more complicated by getting hung up on some of these terms, but if you get that approach down, things are a lot easier, and they'll move you into thermo pretty well. Let me see if I can find one with friction here. I may just find a simple one with friction. Does that have friction? It does. Okay, simple one like that. Well, although this one's even more simple. Here, let's just do this. Just want to keep it simple to start with. Okay. And then you'll see something interesting here that occurs. Okay. I'm just going to slap it on the bottom of this. And I'll just do this. Okay, so here we go. Okay, so if you look at it, it's a 20 kilogram crate with a constant force and direction of that of equal to 100. When S is equal to 15, this crate is moving to the right at the speed of 8. Determine its speed when it's at 25. The coefficient of friction is that. When you're dealing with these, you have to kind of break it down. I'll go ahead and break it down here. So what we've got a weight of, okay, it's 20 kilograms. So it's 20 times 9.81. And this was 100 newtons. So essentially it's 30 degrees there. So you're going to have 50 newtons going up, and you're going to have, what is that, 100 times cosine of 30 going that way. Here, I'm going to do that. So it'll calculate it exactly for me. Okay, it's going to be 86.60254. If you do 100 sine of 30 degrees, you're going to get 50, half of that. So what that means is the normal force, basically, I'm getting this from some of the forces in the y direction equals 0 because the block's not leaping off or going through the surface, not accelerating the y direction. That's going to give you 29.81 minus 50, or this is 146.2. So now this is pulling to the right. Since this is pulling this thing to the right, the friction is trying to slow it down. And it's this 0.25 and 146.2. Okay, let me see if that's possible. It should be, unless it can't read what I wrote. See, it thinks that is a minus. Let me try that again. Okay. Yeah, Okay, so it says 36.55. So good thing this one is larger than that one. So the problem is not ill posed. So if you started pulling at a higher and higher angle, eventually you might reach the point where this component and this component equal each other out and the thing doesn't even move. So now I'll do the energy equation, 1/2 mv squared, and I'm just going to say this can be state 1 plus mgh 1. The block never leaped off the ground. There is no spring, but I'm going to go ahead and include it, plus sum of all the forces dotted with the distance they move through, 1/2 mv2 squared plus mgh. In thermo, they'll really want you to write out all these terms, but they're going to look different because they're going to be associated. They'll still be energy, but they'll be associated with different terms. The concept's the same. It's the energy from state 1 or A to state 2 or B, however they've labeled it. First of all, there's no spring. Those are gone. The block doesn't move up or down against gravity, so that's gone. So what you end up with is 1/2 mv1 squared plus sum of the force dotted with an R equal to the end thing, 1/2 mv2 squared. Now I'm going to go back and look at all the things. Okay, the crate is subject to a force is constant direction. When S is 15, the crate is moving to the right at 10. I don't care if that's 15, 150, 250. All I see, determine the speed when it's S is equal to 25. So to me, state 1 is when S is equal to 15. State 2 is when S is equal to 25, or was it 35? It's 25. He said the speed is 8 meters per second. So that means this is going to be 8. What's the mass for this block? 20. So therefore, this term is simply 1/2. The mass is, oh geez, what was it? 20? And then 8 squared. Wasn't it 20? Yeah, 20 kilograms. So there you go, 20. Now, what are these terms? Well, actually, if you want to be very efficient, or you're supposed to, what you're supposed to do is have this term minus this term, because you want to do the motion's going to be to the right. This looks weird, so I'll do this. Motion is to the right, your R is to the right. The equivalent force is to the right. It's 86.6 minus 36.55. This is to the left, so it's a minus. And so that's going to be your equivalent force pulling to the right. So all you do, okay, I can maybe shrink this down so I can see it and write it at the same time. 86.6 minus 36. I'll make it 6, just because then I just noticed that if I do that, it makes the math a little simpler. Maybe it makes it a little less accurate. And the thing is, it went from 15 to 25. Is that 10? That's 10. So this is the force to the right. That's the distance to the right. Dot product is a positive. And it's equal to 1/2 20 times v2 squared. So suddenly you've got all your information to find everything. I don't know, 10 times 8 squared plus 86 and 36. Isn't that 50? Tell me if I'm wrong. And then this is going to turn out to be 10. So all that divided by 10, and then take the square root of it, and that's going to be V2. So, that's going to be 10.67. So it is going faster here than it was back here. So it went from 8 all the way up to 10.67. So that's all there is in this chapter. There's nothing more. That's it. It's that simple. If you get hung up on things, I mean, don't get too hung up on the fact that he splits it in two. By the way, when you get in thermo, there's always going to be some kind of loss somewhere. It's up to you or the problem in deciding whether you're going to account for it. One of the things you find in thermo, let's say you're shoving steam through a power plant, there's so much energy there and so much at the exit that the losses become insignificant to the amount of the numbers between them. So when you go into that class, you may see there are times that they may say, we'll ignore losses and the energy. So what they're doing is, so the energy level over the losses, you may find like 1%, something like that. So they just say, we're not going to worry about it. And then they'll go on and calculate. But there are always losses, even in these problems. It's just a matter of whether you're going to consider using them. That's it. This is that's 14 in a nutshell. Just like that. These problems, there are problems in this that if you want to solve them the other way, have at it. But like, here's a good one. If you want to solve that using F is equal to MA, I would say go for it. But in what you find out is you're only interested in the energy state here and the energy state here. You care a little bit of what happened in between here, but you don't, if there's no friction, it doesn't matter whether this was curved this way or curved that way. It doesn't matter if there are no friction. So you find out these are state functions, one state and the other state. Sum of forces equal MA means you have to track the particle the whole way through it. And there's a big difference. It makes certain problems not even just harder, makes certain problems impossible to solve. Whereas this, like, oh, geez, this was easy. So that's it. There's none more to it. So I guess what we'll do is we'll do chapter 15 when we come back next time. This is Friday, isn't it? It's no wonder I'm so sleepy. All right. Well, I hope there was some value there in anything I said. If there wasn't, I'm sorry. Uh-huh.
Like we use velocity is speed, the other volume's velocity has different speed.
Oh, does it? So where was the different units there? Oh. Well, okay, so acceleration is meters per second squared. And then the velocity is the, yeah. It's okay. So it's just, the only way I can see where there would be, because F is equal to MA, and if you watch it, this is feet or meters per second squared, but in a way, what we'll see next time. This is something that's really interesting. This is actually the equation, the Newton's second law. And then what we find next time is you just move this over and integrate it, and you move this over and integrate it. So what happens is now you're operating in this off of velocity, which is feet per second. Turns out this believe it or not, these problems are more universal than those problems in that you can solve things that are more complicated. Nobody ever really talked about the fact that the force, say you turn on a motor or something, it starts dragging. It doesn't just immediately create that force. I mean, what happens is you may have, some sort of thing like that before you get to that. Turns out, if you can integrate that with respect to time, you can get the velocity right here. And it's all a function of this integral. And so what we'll see next time is it's like, next time, we actually are going to be using Newton's second law in its original form. And although F is equal to ma works, and you'll find that you can get a velocity at another time, this form is even easier and probably should have been done. So this has other implications like impact, like if a car slams into each other, what happens during that impact, and all sorts of things there. So we'll talk a little bit about that. So just remember feet per second and then feet per second squared. But what's weird is on the left-hand side, your eventual deal is the force anyway. Just really weird. So maybe no one will come and I can take a nap instead. That would be nice, but I think I see somebody coming in. So all right, well we'll see Monday, yeah. I think it's Monday. I'll be awake by then. Probably not, but